And now we move to the second talk. Which is about short-term scheduling of production fleets in underground mines using CP-based LNS.
Hi, my name is Max, and I'm here to talk about underground mine scheduling using constraint programming and large neighborhood search. I'm a scientist at a technology company called ABB, and this is joint work together with my colleague Hamid and with Professor Mikael Johansson at KTH, Royal Institute of Technology. Underground mining is the process of going beneath the surface to separate ore from an ore body, and this ore is then transported up to the surface, where it is typically treated in some kind of concentrator plant. The actual mining activities that previously were manual are in a modern mine mechanized and performed by these types of large mobile machines. So the ore deposits that are close to the surface are diminishing, and this forces mine operations to go deeper to satisfy the market demand. And this is problematic both in terms of safety and in cost of operations. Some of these challenges are addressed by increasing the level of automation on these machines. So lately there has been an extensive uprise of commercially available machines with remarkably high level of automation. And this surge of semi-autonomous machines raises the question whether it is also possible to automate the scheduling of the excavating activities. To give some context, this is a typical planning chain that an underground mine may be subjected to, and the horizon is shortened as we progress downwards here in this pyramid. The life of mine plan has a horizon of, well, several decades. And this is decomposed into extraction plans of various granularity that sets production targets for the upcoming years and months. Short-term scheduling is then the process of allocating resources and scheduling activities in time, and typically have a horizon of a couple of days up to a week. And the goal is to reach the targets that are set by the extraction plans. The two lowest levels here concern the actual execution of the activity. So first you need to route the correct machine to the correct place, and then the actual activity needs to be performed by either manual or automated control. So what we're seeing in the industry is that up here, better plans are being constructed using more elaborate methods and software based on mixed integer programming. And the uprise of autonomous vehicles makes the actual task execution more efficient and predictable. And now what's disappointing in this view is that scheduling is still mostly done manually, and it's a complex, error-prone, and time-consuming activity that has a large impact on the operation. So this work is focused on addressing the short-term scheduling problem using constraint programming and large neighborhood search. So in particular, we present a CP model that applies to several of the most common production methods used in underground mines. So this model builds upon our previous work, but now extends to apply to more production scenarios than before. And the structure of the approach also lends itself to other heavy industries where the production fleet is also increasingly automated. We also propose an algorithm for dynamically adjusting the size of the neighborhoods that are explored by large neighborhood search. So this approach is able to rapidly improve the constructed schedules and has local optimality properties that are beneficial when it comes to real-life acceptance of the approach. And in the paper, we also explore ideas from adaptive LNS and taboo-based methods to further improve the large neighborhood search. So what's the scheduling problem then? Well, there are different ways of excavating ore, and this is called the mining method. And it's the choice of mining method depends on the shape and the inclination of the ore body. So previous work in short-term mine scheduling has focused on methods that resembles this method being displayed here called cut and fill mining. So basically, you excavate the ore in horizontal slices by tunneling your way forward into the ore body. However, this is only one out of many different mining methods that are used around the world, and other mining methods may have other problem structures, most notably more general precedence structures. And in this work, we present an approach that applies to most of the common production methods that are used in small and medium-sized underground mines. Now, regardless of the mining method, the excavation follows some kind of production cycle. So that's a stepwise sequence of activities that needs to take place in order to separate a certain volume of rock from the rock mass at a multitude of locations simultaneously in the mine. So this basically boils down to drilling, blasting, and reinforcing, and then repeating this all over again. But actually, the cycle is a bit more complicated. So first, you drill some holes, then you charge the holes with explosives, you detonate the explosives and ventilate the toxic blast fumes. Then you remove the fully or partially separated rock. And then later, to increase stability, you reinforce the rock mass by bolting the insides to the adjacent rock mass and then by spraying it with concrete. And lastly, the location is prepared for the next cycle. So blasting here is a key activity, and to ensure safety, this can only take place during predetermined time slots during the day called blast windows. And during these windows, no other activities can start, and the operators are typically in secure areas or above ground. As a process peculiarity, this means that we have certain activities, like the ones that involves concrete, that makes the problem contain a mix of interruptible and uninterruptible activities. So some activities can be started before a blast window and continued afterwards, while for others, once they are started, they need to finish before the blast window. And also, some activities leave the location unavailable, for instance, when the concrete needs to cure, while the machine is free to do work elsewhere. And in addition to this, machines are also shared between different steps in the cycle. And since the underground road network can be vast, it's important to accommodate for travel times between different locations. The scheduling problem we study is then based on taking the activities that are to be scheduled on different locations and produce a feasible schedule that allocates machines to these activities and schedules these in time, respecting a couple of process constraints and safety constraints. This means that the scheduling data consists of the locations and their pairwise distances, the machines and their corresponding job eligibility, and a list of jobs being the atomic activity being scheduled. So each job is characterized by the type of machine it requires, where it is to be performed, and the nominal duration of the job. And also precedence constraints are plenty in this application due to, for instance, the production cycle, but also due to safety and layout restrictions. The model that we have adopted is based on these decision variables. So we have the start time of each job, the execution status representing that if OJM is equal to 1, then job J is executed by machine M. And we use precedence order variables where we introduce these Boolean BJJ prime to encode that if BJJ prime is equal to 1, then job J precedes job J prime on the same machine. And similarly, C encodes the same thing here, but on the locations rather than on the machines. I will now go through a couple of the model constraints. So first, we enforce that only one machine is allocated to each job and that only eligible machines are used. Then we deal with the mix of interruptible and uninterruptible activities due to the presence of these blast windows. So to enforce that uninterruptible activities never intrude on the blast window, we directly restrict the feasible domain of the corresponding start times. And for the interruptible activities, we maintain two timelines, so one real timeline and one compressed timeline. So the activities are scheduled in compressed times and later post-processed by introducing the blast windows to solve the original scheduling problem. And this is possible since the same machine is used both before and after the blast window. The cumbersome part of this approach is, well, having two timelines you need to figure out how to express the temporal constraints in the compressed time domain. Some more process constraints relate to making sure that blasts only take place during blast windows General precedence constraints relating to, well, among other things, the presence of a production cycle within each location, and also make the presence of cure time for the activities that involve concrete. To make sure that the machines are treated as disjunctive resources, we introduce these precedence order variables. So we constrain the bjj prime variables to take values 0 or 1 if they are scheduled on the same machine. This indicates that they need to be ordered, right? And they take a dummy value if they are scheduled on different machines. So bjj prime is equal to 1 here means that job j precedes job j prime and there is sufficient travel time to go between these jobs. Similarly, precedence variables are used to enforce disjunctive execution on the locations also in the production scenarios where the order of execution is not fully specified. The objective function that we use have been formed through discussions with different mine operations. So we have found that using sum of location make span is a good metric, and this is defined as the sum of each location's individual completion time. So this objective obviously relates to the make span that is commonly used to represent high machine utilization. But it also relates to the sum of weighted completion times that sort of minimizes inventory cost or holding cost of the schedule. And in mining, both of these objectives are important. So typically there's a cost related to having a location ready for production. And there's also a safety aspect related to having many production areas operational simultaneously. On the other hand, one would like to use the production machinery as good as possible. And this objective also makes sense considering how short-term scheduling is situated in the planning chain. The search strategy that we employ is based on first using a greedy load balancing machine allocation heuristic. And then we follow that by branching on these precedence order variables in a manner so that basically the jobs are ordered from early to late given the current minimum value of the start times. And once we found a feasible ordering on both machines and locations, then we simply set the start times to the lowest value of their feasible domain. So using this model and search strategy, we can generate quite okay schedule using restart-based search. And this is a problem instance with a bit more than 200 jobs over 20 different production locations. And this is scheduling data from an operational underground mine in Sweden. However, we have noted earlier that large neighborhood search can be used to quickly improve these schedules when it comes to the objective value. In general, for LNS, it's crucial to have a good neighborhood definition. And we have found that location-based neighborhoods work well in this setting. And we attribute this to the many precedence constraints inferred by the production cycle within each location. So these constraints make the other neighborhood alternatives that we have explored simply too inflexible to contain any improving solutions. Our LNS approach is based on randomly selecting a subset of the locations represented here by these shaded areas. And then we relax all the variables, the machine assignments, the orderings, and the start times that correspond to the activities that are scheduled on these locations. We then search for improving solutions within this restricted search space. And if we found an improving solution, we accept that one. And if no better solution is found, then we randomly select a new subset of locations. So the neighborhood size then correspond to how many locations are relaxed. And in our earlier work, we have used different fixed neighborhood sizes, and we found no dominating neighborhood size. And this is due to the inherent trade-off in exploring, well, in larger neighborhoods, you can potentially find better solutions, but it may take a very long time to find them. So therefore, in this paper, we propose to encode this in an algorithm to adapt the neighborhood size automatically while solving. So basically, the idea is to start off small, relaxing only 2 locations and solving the resulting neighborhoods exhaustively. And then we increase the size as all small neighborhoods have been searched, but with one exception. If a solution is found, we start all over again from small neighborhoods. And this comes with a couple of benefits that I will now briefly demonstrate using this example run. So the red dots here are objective values, and the green line here corresponds to the neighborhood size. The blue dashed line here is where a fixed neighborhood size of 2 would have stagnated. So we start off small here and find some initial improvements, but we need to start scaling to larger neighborhoods to find more improvements. So here we can see that after we find a solution at size 4, we have many subsequent solutions in smaller neighborhoods. And this is the reason for scaling down again and restarting from smaller neighborhoods. So we have found this to be beneficial since the search space grows very fast with the neighborhood size. And this makes it important to have a tight upper bound on the objective before scaling. And in practice, what happens if we only increase the size, which sounds like a reasonable strategy, then we spend too much time on solving these larger neighborhoods in contrast to the improvements that we find. And this approach also has a benefit when it comes to explainability. So say that the algorithm terminates here at n equals 4. Then we can guarantee to the mine scheduler that receives this that you can try as hard as you want, but you cannot find a better schedule without changing the activities on at least 3 locations. So the approach then removes these obvious improvements that otherwise skilled manual schedulers could easily spot. And this makes it easier for the scheduler to trust the constructed schedules. This is an example run. Now the highlighted nodes here correspond to the relaxed locations, and the distances between the nodes represent the distances between the locations in the problem instance. So this is on synthetic data that contains, well, 100 jobs, and the arrows here correspond to precedence constraints. And as we can see, there are only a couple of locations that are affected in each iteration, but we still manage to find improving solutions. In this example, we were able to reduce the objective by 25% from the first feasible solution. This model has been implemented in G-code, and we compare the performance of this model using instances that are derived from 2 different types of mines having different precedence structures, and also on synthetic generated data. So the green line here corresponds to the LNS with adaptive neighborhood size. And we can see that it rapidly improves the scheduling quality, at least compared to a restart-based approach in these cases. So, wrapping up, we have first presented a CP model that generalizes previous work in short-term mine scheduling to apply to more production scenarios. Most notably, we support more general precedence structures. We have also proposed an algorithm for dynamically adjusting the location-based neighborhood size. And this approach comes with benefits both when it comes to solving performance, but also it increases the potential of real-life adoption. I further invite you to read the paper, where we also discuss different ways of selecting what neighborhood to search given the neighborhood size. And we find that a taboo-based approach appears promising. And throughout the paper, we demonstrate the performance on instances derived from real operational underground mines. And with that, I would like to say thanks for listening to this presentation.
Okay, many thanks for the presentation. There's time for one quick question. Mikael?
Yes, so this was very interesting. A small question about the model. Is it always the case that jobs require exactly one machine, or is this a simplification you made for solving problems in practice?
So in this case, that's in the mines that we have studied in this case, that's for sure the case. But there are scenarios when that's not the case as well. But we have not explored that in detail, but we think we can expand the model to support that as well with quite easily.
And then also a small question about the model. You have lots of binary variables. Did you also try with integer variables instead?
Yeah, we explored more of a grand tour approach as well. We found in this particular case, we found this model to perform better. But I think it's time to go back and revise that as well.
Okay, thanks.
Thanks.
Okay, are there other questions? So I have a quick one. So from what you said, it seems that you don't put a time limit on the exploration of each neighborhood, right? So you are exploring every neighborhood to completion. Have you considered introducing a time limit at least for the first iterations?
Yep, we have considered that, and I mean preliminary results are quite promising. On the other hand, you lose the explainability argument if you don't introduce it later on in the solving procedure.
Exactly, but you could adapt it like you do for the size. You could do the same as having a schedule for a time limit, and
yeah, I think that's a good approach actually.
Okay, so thanks again. Let's thank again the speaker.
Thanks.